pleased to have our speaker here today. It's Dr. Robert Van Buskirk, who is from Lawrence Berkeley Lab, where he's been since 1999, I believe. He works in a field called energy policy analysis. He's taken to heart our discussion of what physicists do, so we're going to hear how he brings a physicist's problem solving to these issues of energy. His degree, he has both a physics and math degree from UC Berkeley, followed by his PhD in physics from Harvard. He's a world traveler, having spent time in the East African country Eritrea, both working as a professor there and then working in their energy policy, in their Department of Energy. Also having spent some time in Asia, Beijing and Hong Kong, before coming back to the Bay Area, where he works at Lawrence Berkeley Lab. So I am very pleased that we're going to hear a physicist's perspective on clean energy technology. Let's welcome Dr. Van Buskirk.
Thank you very much. One of the things I hope to communicate is how physicists can have almost too much fun doing physics in many places where he's not supposed to be doing physics. So, so just to the key skills. So I am the son of two math nerds who met in badminton class at UC Riverside. So and my parents are very happy that I grew up to be a math nerd too. And I would do math contests in high school instead of sports. And when I went to college, I double majored in math and physics and decided, oh, I'll go into physics because the word problems are easier in physics than the proofs are in math, right? And so that's how I sort of got into physics. And the key skill that has benefited me and allowed me to provide value to the people around me is basically helping people translate reality into mathematics. Because when you can get reality formulated into an equation, if you happen to have the right equation, then that equation can be used to predict what will happen in new situations and new conditions. And that ability to predict what will happen in new conditions really is what people around value a lot. So reality to math, or math to reality, and then using that math to predict what will happen really is a key skill of physics. And then the reason physics is a little better than pure mathematics that way is that physics is sort of the most mathematical of the sciences, but it also does have the experimental verification that your math works, right? So when you're in math, you're sort of working with pure deduction, right? From these assumptions, does it lead to this wonderful artistic theory? In physics, at the end of the day, you say, the real test of whether or not my equation is the right equation is if I can do a controlled experiment and I can test whether it's wrong or not wrong. And if I have an argument with my buddy about whether or not his equation is better than my equation, we can set up an experiment and prove who is right without arguing about it forever, right? How many arguments are perpetually unresolved because you can't verify, you can't determine them through an experiment? So those are the key things. Mapping equations to reality, and then eventually being able to determine which equations are correct through hypothesis testing in an experiment. So what have I done? Now this is, all these things is more a testimony to my attention deficit disorder combined with my age, right? So I'm over 50 years old, so I've been able to run around doing physics for 30 years at least. And one of the first things I did is chaos theory was up and coming in Berkeley, so I did my undergraduate thesis on measuring chaotic dynamics in electrical circuits. At the same time, I would travel to Nicaragua, and there was a mechanical engineering professor. We'd go do water projects. After that, I did my PhD on the red spot of Jupiter. Again, it's fluid dynamics. The red spot is a giant vortex. I spent 2 or 3 years showing that I could solve the math equations on the computer to 1 part in 100 trillion with only a couple hundred data points, right? So get exponential convergence of my mathematical equations on a computer, that sort of obsessive impulse to calculate things better than anybody else has calculated them before, to measure things better than anybody else has measured them before is another part of being a physicist. So then, after Harvard, I was a little tired of grad school. I had a friend who was doing water system calculations for Native American water rights. I joined that company for a while. That company was owned by someone from Eritrea, East Africa. And Eritrea, East Africa had just gotten its independence. So I asked my boss, can I apply for a Fulbright to go teach physics in Eritrea, East Africa? So I got a Fulbright. I taught physics in Eritrea, East Africa for a year, and they were just starting their Department of Energy. They were just starting their renewable energy program. And the head of their renewable energy center said, can you please come to our center? So I went to their center for 3 years, and we started setting up clean energy programs in a small little research center in a small little country off in the east of Africa. At the same time, my partner, my girlfriend, had to finish her studies in the US. There was no electronic mail system, so we set up the electronic mail system for the country. So I could write her every day because I was on a local salary of only $200 a month. Letters took 2 weeks, and phone calls were $2 a minute, so I needed email. So after that, after I set up the email system for Eritrea, one of my colleagues from the water rights company said, I want to go to China and do computer telephone startup business in China. Can you come? I said, I'm tired of traveling. My partner said, I'm not tired of traveling. And we went to China and did the boom bust thing. It was a startup company. The CEO was a little corrupt. And so the company crashed after a year, and I came back to the U.S. When I came back to the U.S., I went to Lawrence Berkeley National Lab, which is the national. I'm not sure how many people know what the largest research institution in the world is. The largest, yeah.
Isn't it the University of California?
No. It's the Department of Energy National Laboratory System. The U.S. Department of Energy has more than a dozen national laboratories with more than 1,000 scientists in each laboratory. And so the U.S. government, and this comes out of the Manhattan Project ultimately. So the U.S. government runs a research laboratory system with more than 100,000 scientists spread all around the country who are researching everything from biology to nuclear weapons to clean energy to astronomy. So that is, actually, that's in terms of what physicists do. That may be the one thing, most useful thing you learn, is that there is a national laboratory system run by the Department of Energy that employs 100,000 scientists. That's one place you may want to look to for going your job. So I went into a place where we were calculating the regulations for your refrigerator and your appliances. benefit cost. While I was doing that, I still was traveling to Africa. So I hooked up with some friends in Ghana, developed a collaboration in Ghana. We set up refrigerator efficiency policy in Ghana. I had some friends in Senegal. I helped their mangrove reforestation programs develop a way of getting carbon credits for reforesting mangroves. And I have an aunt and uncle who does organic farming in Santa Cruz. And there's methyl bromide for strawberries. What we did is we created a small little organic company to ferment sort of soil beer and strawberries, something called anaerobic soil disinfestation, and we came up with an organic alternative to chemical fumigation for strawberries in Santa Cruz. So that was one thing, and then I partner with universities for green buildings. I have another friend who does solar lights and stoves, and all that is just taking the scientific method and having the hubris to go out into the world and try to solve a problem. Okay, so now there's all that fun stuff. I'm going to now dive deeply into the issue of technology forecasting. Okay, so how do we do technology forecasting? So one question is, isn't all this green technology just too expensive, right? How are we ever going to solve climate change? Well, one of the approaches, and actually the approach of Stephen Chu, who was appointed as the Secretary of Energy at the beginning of the current administration, he began his career in Bell Labs. And Bell Labs invented all sorts of technologies that have transformed our society. So he approaches the climate change problem with the philosophy that if we're creative, if we can accelerate the technological innovation process, then we can make the clean energy the cheapest energy. And if the clean energy is the cheapest energy, then it'll be much easier to convince people to switch from fossil fuels to clean energy. So his whole task, his whole push is to accelerate, and actually still the current push of the Department of Energy is to accelerate innovation in the clean energy sector to make it cheaper than any other alternative, so eventually we all migrate to clean energy. So the question is, what are the laws? What are, in some sense, what's the laws of physics for clean technology prices, and how do you determine those laws? So we start with a concept of the fastest moving technology. The fastest moving technology is computer technology. And the law we have, which is an empirical law, it's not determined by physics per se, is Moore's law. And Moore's law says every, whatever the time period is, every 18 months, the density of transistors on a chip doubles. And that law has been going on for 50 years, and people have said it's got to stop, and it hasn't stopped, right? It's been this sort of self-fulfilling prophecy. So if that's our sort of mythical example of a technology innovation law, how do we build that law for green energy technology too? So I'm going to go through that sequence of calculations and data on that, and I may go through it a little too fast. So you'll have the slides, and I'll answer questions. So here's Moore's law. Moore's law, you have transistor count versus date of introduction, and it's a nice exponential thing. Number of transistors doubles approximately every 2 years. No, Gordon Moore was an engineer, not an economist. And I can tell you that when you're a physicist and you go and do economics, the economists might not be very happy. So, if you actually look at the light output of whatever our lighting device is per unit energy input, and you go back a couple hundred years, you actually find out that the output per unit input for that lighting device also follows an exponential law, right? Now you have to go back longer. The exponent isn't as big, right? But there is this sort of technological trend which gets it going faster. And that exponential law is that the light per watt of input doubles every 25 years. And you can go back, there's refrigerators. So this is the US refrigerator graph. And what happened in refrigerators is when refrigerators were first invented, there were these little electric ice boxes, right? And for the first 30 years of refrigerators, it's just bigger is better, right? I want a bigger ice box, I want a more capable ice box. So what happened is they were putting more and more energy into it, but just to make the icebox better. There was no consciousness of the energy use of the refrigerator at that point. They just wanted it to work. What happened is, in the 1970s, we had the Arab oil embargo, and we had an energy crisis, and California started implementing efficiency regulations for refrigerators. So then they started being conscious about the efficiency of a refrigerator, and the curve changed. And with the implementation of labels and awareness about energy efficiency of refrigerators, that curve changed so that now the efficiency of refrigerators increase at 4% per year. Similar thing happened in Europe. Europe was a little behind California. They didn't implement their refrigerator regulations until about 1998. This plot is the percent per year decrease in energy use for refrigerators in Europe. And so before there were any regulations, it dropped about 2 or 3% per year, and then with the European regulations, the energy use of refrigerators has been dropping about 5% per year. So again, these sort of exponential trends. Basically, with standards and labels, refrigerator efficiency appears to double every 15 to 20 years. So now, okay, so now I'm going to try to explain a mechanism for these trends. And I don't know how many have people heard about learning curves? Right, so I did one experiment on the learning curve. I had this Excel spreadsheet, and I had to cut and paste something about 50 different times. It was a complex 10-step cut and paste, and so I said, well, I wonder if I'm on the learning curve, right? Because it's a painful cut and paste. So I timed how many seconds it took me for each of one of these complex cuts and pastes. And I noticed that as I kept doing the task, I would sort of experiment with different orders of doing the things to come up with faster and faster ways to do the complex cut and paste. And that my experimentation, the fact that I would try something, and if it was better, I would keep it, right? And then try something better, actually put me on the learning curve. Right, so I did that little experimental thing. I did the data points. I checked to see whether or not the time for the task decreased as a power law of my cumulative experience, and I found I was on the learning curve. Now let's see if I remember this correct. So with that experiment, like a good physicist and mathematician, I said, okay, let's develop a thought experiment. Let's see if we can derive from first principles what a learning curve is. And I said, well, I'm experimenting with different ways of doing something. Well, if I'm doing that, there's a range of possibilities. So I have a probability distribution that represents all the different ways this thing can be done. So I'm going to assume that there's a series of ways of it being done. It's a probability distribution. I assumed a particular form, log normally distributed in its performance. And I said, can I derive a learning curve? So I was sitting on an airplane. I had my Excel spreadsheet. I built a model. I said, randomly pick from a log normal distribution. If it's better than what I did before, keep it. If it's worse, throw it away. How fast do I learn? And I got a learning curve. So that simple thought experiment regenerates the process of a learning curve. If you try stuff in business, in startup businesses, it's called fail fast, fail often, fail cheap, right? Keep trying stuff, keep what works, throw away what doesn't work, and keep going. And that puts you on a learning curve. A learning curve, so now if you're trying a bunch of things, you do something better, you grow your business, you try a few more things, you do something better, you grow your business more. What happens is you create an exponential feedback. Every time you do something better, your business gets better. As the business gets better and bigger, you get to try things more frequently, right? And that gets better. So a learning curve combined with exponential growth provides a Moore's law. So now we have, just using simple physics-style mathematics, we've derived Moore's law. These are some plots of my calculations. Let's see, log normally distributed, right? And so those are little samples I did. The wider the range of your possibilities, the faster the exponent of your learning curve, right? Because there's more upside potential that you can sample from. So I spent a few years back at DC. The Secretary of Energy was curious. He said, well, let's study what's been happening with technological learning for something as mundane as clothes washer efficiency. And so what we did is we plotted the real price of clothes washers in two forms, right? The red squares is just the first price. But the first price isn't the whole price of an appliance, because you also have to pay for the water and electricity. So when you add the water and electricity into the price, that's the life cycle cost. So those are the blue squares. And what we did is we plotted those trends before any labeling and standards, which is before the circles, and after labeling and standards. And we found that when you made the markets, when you made the policy, when you made society more conscious of the environmental impacts, then not only are you decreasing the cost of the water and electricity, but you're creating the motivation, you're increasing the motivation for innovation in general, and you accelerate and sometimes you accelerate the learning curve on the product itself, right? Because people are trying more things more often. So okay, and that's the refrigerator one. I'm going to skip that. Now, so then, even though I'm a physicist, I have read a little bit of economics. And so one of my economist friends said, there's this guy named Baumol who wrote in the 1960s what happens to prices when you have a technological part of the economy that's moving faster than other parts of the economy. And he says what happens is, because labor is mobile, right? someone says, oh, my brother, he works in a factory, he makes $30 an hour. Even though I'm in a retail store, I'm not going to work I'm not going to get 1/10 of what my brother gets. If his salary goes up 20%, I want my salary to go up at least 10 to 15%, right? So labor rates for similar skill levels tend to be the same across different sectors of the economy. But when you have an area of the economy where it's innovating very fast, both in production and in quality, what happens is the quality you get for the product per unit labor input increases, right? That's the productivity increase of that sector of the economy. If the labor cost is roughly the same, and the productivity keeps increasing, what tends to happen is the high productivity increasing parts of the economy have prices which drop fast. We see that in computers, right? It's like, why should I buy a computer today? If I wait a year, I'll get a better computer for cheaper. And that's because Moore's law has this consequence in the price trends of the product, quality adjusted price trends of the product. So similarly, if you accelerate innovation in the clean energy sector by Baumol's theory, the clean energy products get cheaper faster. Right? So this is just a bit of an illustration that, so you can go to the Bureau of Labor Statistics, you can download price indices. You find that service sector, which is labor intensive, prices go up. Durable sector, household appliances, which have more innovation, prices go down. Over the last 60 years, prices have gone down by a factor of 4 for household appliances, right? It's that innovation that creates the room for those products getting better and better. If you go to the very fast-moving sectors of the economy, computing sciences, televisions, electronics, you see that some of those over the past 50 years have dropped their quality-adjusted prices by a factor of 100. Right? There's no way you would have, that 60-inch stellar high-resolution TV back in the 40s. It would cost you $1 million to make something like that. Right? So yeah, innovation directly affects prices. So then, am I going to go over this? I'm not. This is a little too much, but why don't I? Okay, so now I'm going to go over this a little bit to tell you how technology innovation in products leads to increasing efficiency. So this curve is an energy use versus price curve for refrigerators, for example. Okay? And the idea is, a cheap, inefficient refrigerator is easy to build, so it's cheap. But if you add insulation and put a better compressor in it and all that stuff, it's more expensive to build. So as the energy use goes down, the price goes up. Okay, so you can use that curve to calculate what we call the cost of conserved energy. How much more does it cost you to make a better refrigerator to save a kilowatt hour of energy use on that refrigerator? So this is, delta price over delta EU energy use times your payback time. How many years of payback time is your cost to conserved energy? And what's going to happen is your optimum efficiency for an appliance is where the cost of conserving energy is equal to the cost of supplying energy. That's your balance point, right? So the key thing is, if the technology cost of the appliance is dropping rapidly, then the cost of conserved energy is going to drop rapidly. And if the cost of conserved energy drops rapidly, then your balance point where the cost of new energy equals the cost of saved energy is going to move closer and closer to zero. So that is how technological innovation in your regular household appliances leads to higher and higher efficiency of those regular household appliances. And we see that reflected that when Europe started adding the level to an efficiency label to TVs, those TVs improved their efficiency at 10 to 20% per year because the TVs are innovating at that really fast rate. Right? So now, so those are details. You know, do a power law equation for that curve. You can calculate the equilibria. More equations, and you know this is when the cost of conserved energy is equal to the cost of electricity. Then this is the equation. Price of appliance, that's the curvature of the curve. That's the payback period, and that's the cost of electricity. So you can write equations for all that, and that's the equation. The minimum cost energy use is that. So if appliance prices decline relative to the price of electricity, if the elasticity price with respect to energy use and payback period are roughly constant, then efficient appliance energy use declines at the same pace that the quality adjusted appliance price declines. Okay? And so that gives you a law for, you know, how fast the clean energy properties can improve. And so what happens is, if you want to see where efficiency is going to where compared to where efficiency has been, right? Here's the equation. It's the payback period under the new conditions, the price of electricity under the new conditions compared to the payback period under the old conditions, and the price of electricity under the old conditions. And with this exponent that depends on the curvature of the cost. Now, I want to explain how this equation means that the solar off-grid electrification of Africa may very well be one of the primary determinants of our future super efficient appliances. Okay, and I'm not sure I explain it well in the following slides, so I'm just explaining some of it in words. If you look at an off-grid solar system right now, it needs a battery and a solar panel, and the cost to get 1 watt-hour of electricity per night is about $2. So if you get 100 watt-hours per night from your system, it costs about $200. $200, right, to buy the system. So now, if in Africa that payback period is going to be just a couple of years, right? So if it's costing you $2 per, say your payback period is 3 years, right? 365 days in the year, 3 years, a little over 1,000 days, right? 1,000 days times a watt hour is about 1,000 watt hours, which is a kilowatt hour. It costs you about $2 per kilowatt hour to provide off-grid electricity in Africa. Okay. Now, what do we have here? We have 20 cents a kilowatt hour. Okay. So in Africa, they have $2 a kilowatt hour for the villages that are off-grid. Okay. That means the efficiency, this number, say, is about 1. Right? So the efficiency that's required in rural Africa is approximately 10 to the 1/2, which is 3, right? So Africa needs appliances. Africa needs devices that are 3 times efficient than what we have here. And there's 1.5 billion people who don't have electricity. So now what happens, which is equivalent to 300 million households. So we have 300 million appliances to sell to people who have solar off-grid systems. And they need stuff which is 3 times as efficient as it is right now. Okay? If we can get Africa and the rest of the off-grid developing world electrified over the next decade, then 10 years from now, our stuff will be 3 times as efficient as it is right now. Okay? So, go ahead.
I mean, to me, this is like an epiphany because you look at this and the first world says, "Oh, we've already got what we need, right? We're middle class and so on." And then you go, "Oh, China's polluting." I'm speaking broadly, and of course, none of this is correct. To some extent, "Oh, China's got all of its technological advances." And that is, look at the pollution that's happening. That's an environmental disaster. I mean, I'm taking it with a grain of salt. I'm just putting forward ideas. But this model is saying making parts of the world middle class drives the exact technological evolution we need in the appliances for us all to have a lower footprint on the world. Is that a way of taking what you just said?
Yes.
Okay, exactly.
And Africa got cell phones before many of us did, right? Why did it get cell phones before we did? Because they didn't have the money to build the telephone networks, right? So they had to leapfrog from the old technology to the new technology. Similarly, they don't have the money to run power lines everywhere. They're going to have to get their electricity with solar panels and batteries. And if they're getting their electricity with solar panels and batteries, they're paying $1 to $2. They're going to be paying $2 a kilowatt hour. And if they're going to be not buying a system that's too expensive, they're going to need the appliances that go with that solar panel and batteries to be 3 times as efficient as what we have right now. So, and you see that right now. Okay, so these are fluorescents, which are nice. Okay, they have about 40 or 50 lumens per watt. Okay, the light bulbs that are going into households with solar systems in Africa now have 100 lumens per watt because they can't afford. This electricity is 20 cents. They can't afford the electricity at all. They will buy a light bulb that's 2 to 3 times as expensive as that, so that they don't have to buy so much solar panel and battery. So that is, that's the physics of innovation, and it's pointing to a future over the next 10 years, where, in some sense, the limit to improvement is your and everybody else's ability to innovate a little faster. So, and I think I'll end here. Let's see, what were the other slides? Yeah, so these are just the improvement rates that are going to be needed. They have to go up to the television, cell phone improvement rates, which are like 10% per year. And that was sort of the summary. That's it.
Well, we got time for questions.
So who are the people that are making all these, more efficient appliances? I mean, how do you motivate the normal companies to do it, right? Is it like other companies that are concentrating on the market in Africa, or?
There are a whole bunch of folks in the space, and it's sort of like computers, right? You don't know which company's going to win or which company's going to have the right product, right? Is it going to be the Apple, or is it going to be Microsoft? Is it going to be the Seagate, or is it going to be the, what happened is, as those innovation rates accelerated, you actually had a faster turnover in the details of who was involved. And I expect that as this market grows very fast, you will start seeing a bigger churn and turnover in the details of who is building what. So Philips is very involved, Osram is very involved in the lights, but there's Chinese startup LED companies that are coming in and might disrupt them, right? So there's, I think the short answer is, yeah, there's a bunch of incumbent players and there's a few startups. Probably what we know is that the landscape 5 years from now will be completely different from what it is today.
How do you account for the possibility that Africa just gets cheaper energy? I mean, what if it goes from $2 per kilowatt hour down to $1.50 there for whatever reason? What does that do to the model?
Yeah, so that'll happen. That's probably where it will, what will happen is there'll be some innovation on this price, which will drop the motivation for efficiency. But this price right now is sitting at about 10 times what our price is. So even if this drops down to only 4 times as much, the efficiency that's required is about twice as much as what we have right now. Yeah.
Can you just explain what the factor epsilon is?
So that epsilon is this slope. So when you do a log, So the cost of conserved energy is the slope of the price versus the energy use. And so you take this curve and you take a derivative and then you plot cost conserved energy versus energy use. And the epsilon is related to the slope of this curve on a log-log plot, right? So it is that exponent which describes the curvature of the price efficiency relationship.
And so a typical value for epsilon is?
Between 0.3 and 1.5. And usually for refrigerators it's 0.6. For lots of things it's about 1.
Dr. Van Buskirk, how do policy, I mean, this is physics. This is physics that, as you said, touches on economics. There are models of this which are sort of more macroeconomic models. And so you're also, in something like this, dealing with something that people are interested in for policy reasons, and what should our national stance be towards efficiency standards and labeling and all of these things. But you come from a sort of technical background, and these are things that policymakers might say, well, we might want to do things differently. And so I'm just wondering, how does it feel to navigate that world, that intersection between going through this and coming to this understanding, needing to relay it to other people, and then having them say, it's not on our agenda for a strong African middle class that drives technology innovation, but there are companies that see this and say, no, this is a place to be transformative.
Well, in some sense, you've answered your own question, right? So you put out the science, and then when you put out the science, you never know exactly how it's going to be used or who's going to use it. So the folks who have been doing things a particular way for the past 10 to 20 years don't want to change necessarily. But there are institutions that are charged with solving some problems. So the UN has an initiative which is called Sustainable Energy for All. and that Sustainable Energy for All initiative has adopted the idea of doubling the pace of progress on efficiency as a way of also enabling increased electricity access to those who don't have access to electricity yet. So if your end users use less electricity, then it's cheaper to provide electricity for people. So what happens is, it's accepted by some, in some very enthusiastically, and others don't want to hear it and want to keep doing things the same way. And you try to advance the science with your most enthusiastic customers.
On the energy production side, it seems like there's a lot of innovation taking place there with the solar panels becoming more efficient. Just last week, Elon Musk has the new gigafactory that's going in Nevada. Do you think that is like trending along more exponential innovations as far as energy storage technology and energy production?
Yeah, so I think that the energy production side is actually many of the technologies are similar, right? And a lot of electronics and power electronics, etc. And so I think they're both going to innovate in the around 10% per year, 10 to 20% per year improvement level, and that the cheaper supply will meet the cheaper efficiency, 5 to 10 years out, and then I'm hoping we're at a place where clean energy keeps getting cheaper, so we come up with more productive uses of clean energy after that. So.
Other than solar panels in Africa, were there any other means of clean energy big projects they were working on in Africa for providing them energy?
Well, Africa has a very large amount of less developed hydro potential. So there's billions of dollars of investment being thrown at some of the hydro developments. The drawback is you dam a river, you're changing the environment behind the river. So a solar panel on a village hut has a little less of a footprint. Though the batteries are still pretty bad. So.
Actually, that was what I was going to ask you. Is there any sign of this kind of efficiency improvements for batteries? Because batteries seem to me to be always the big problem with any of these kind of systems, that people just can't seem to make a kind of battery you really like. It doesn't weigh as much as your car to run your car.
Well, so the lithium iron phosphate batteries last about 5 to 10 times as long as the old lead acid batteries, and they're about 5 times as expensive. And so you're seeing some of the systems in Africa converting over to the lithium iron phosphate batteries. So basically, the battery technologies which are being developed for the cars will spill over to produce lighter, more powerful batteries for the end user in Africa. Though there'll still be the issue of getting the used batteries back to the recycling centers so that the lithium can be reused rather than polluting the environment.
You seem very positive about these things. You have a jovial spirit about this whole thing. And to be honest, I'm taking it as a positive. You hear energy talk and you go, what are we going to hear about how difficult things are for us? Am I interpreting this wrong and there's so many hard different things? Or is there a sense that when you pursued this, you found this and thought, well, this is nice, there's a natural mechanism to push towards efficiency in this way? I mean, are you in general positive about energy outlooks for the world?
Well, full disclosure, my friends call me the designated optimist. So my job is to be positive, and in some sense, my dad said, just look at things logically, right? So you go to the talks about climate change and you say, there's the developing world, it's growing so fast. How can you possibly solve climate change when the emissions are growing in China so fast? Well, do the math, right? Okay, the emissions from the developing world are growing at 5 or 6% per year. Okay. Well, that means the clean energy has to grow at 10% per year. So, how do we get clean energy to move at 10 to 20% per year? And therein lies the solution. Right? It's, getting from point A to point B may not be so simple, right? But the logical path of emissions from fossil fuels are growing too fast, and you say, okay, well, clean energy has to grow faster. How fast do we have to get clean energy to grow? And let's figure out how to grow it that way. So, it's
Well, at least it's a path.
It is a path. It's nice to have something that's a possibility.
Right.
So, China is as big of a population as the 1.5 billion people in Africa, right?
Yes.
So, what's going on in China that could sort of lead to that faster growth of renewable energy versus fossil fuels?
China wants to beat the U.S. at selling to the customers in Africa. So they have a strong motivation to develop the clean energies.
Yeah, so we might have some students sitting in this room really thinking to pursue a career in that field of clean energy or green energy in 1 or 2 or maybe a few years. Do you have anything particular to say to these people so they can really are ready or will be ready when they graduate to jump into that big field?
Start buying solar cells now, start buying batteries now, start buying lots of little devices, start putting them together and building things so that when you go into the clean energy field and they start talking about all this stuff, you have hands-on experience and you know exactly what's being talked about. Because it's just, you can go on Amazon and buy a bunch of solar cells for $50 or something, right? There's multimeters and batteries. You can, what did I do? When I went to DC for 3 years, I rented a room. And I said, oh, well, let me take my electronics off grid, right, in the room. So I just got a couple 10 watt, 25 watt panels, put them down, did a battery, controller, ran my laptop off it, my lights, my cell phone charging, and now I know how to do an off-grid system, right? And it costs only a couple $100. So all that's very possible, and stuff is getting better all the time, and the information's always on the internet, and there's 1,000,001 things to invent because we have 200 years of history of people. Or I guess 100 years of history of people inventing things for fossil electricity, but it's only recently that the solar cells have gotten cheap enough that you can build who knows how many devices out of little solar cells, right? So now you have that 100 years of invention that can be reinvented for a solar electricity supply. Now take all that stuff and reinvent it for the clean energy case, and there's plenty to do. So.
Let's thank Dr. Van Buskirk.